Hi, I'm Brandon Graisley. I'm a high school math teacher. We're going to solve linear systems by substitution. This is part 2, and in this case we're looking at examples where we have lines that are parallel to one another. And there are two situations that can happen. You can have two parallel lines like this that don't touch each other, or you could have two parallel lines which overlap one another. They are the same line, they're equivalent, and so they touch everywhere. They have infinitely many intersection points. So let's look at a couple of examples, one of each. And so the one I want to start with is this. There's a line, and here's another line. Possibly. It's certainly going to be parallel, and we'll figure out whether it's there are two parallel and distinct lines, or if they are actually equivalent lines. So once again, if x1, y1 is an intersection point, then what must be true? Well, if they're going to intersect, then we must have that y1 equals 3x1 minus 5, that is, it's on the first line, and 6x1 minus 2y1 plus 3 equals 0. It's on the second point. So I've substituted the intersection point into each line. Both equations must be true. All right, well, let's continue from there. I'm going to substitute this expression for y1 into this equation. That's the substitution step right there. Let's rewrite this equation now, replacing the y1 with an expression for y1. So 6x1 minus 2 times, not y1, we're now going to write 3x1 minus 5 plus 3 equals 0. And we start to simplify. 6x1 minus 6x1 plus 10 plus 3 equals 0. Well, these two here, 6x1 minus 6x1, that's 0x1, which is the same as saying 0. And then these will be 13. So I just have 13 equals 0. Well, hold on just a second. That is not true. That is always false. And it's for all values of x1 and y1. That is, it doesn't matter. Oh, I'm sorry. It doesn't matter which values you try for x1. You'll never get a corresponding y1 that is on both lines. That gives you a point on both lines. So what that means is, look at how we began this. If we have an intersection point, then here's our logic. This thing must be true, but it's not true. So we do not have an intersection point. We started with a faulty premise. So we assumed there must be an intersection point. We found out that the universe is broken and things don't really work anymore. Okay, perhaps there isn't really an intersection point. So that means that these must be two parallel and distinct lines that never touch anywhere. That's how it works. And this statement here, this is me explaining. You don't always have to write something like this, but what you should instead write is something like the lines are parallel and do not intersect, or perhaps the lines are parallel and distinct, or there is no intersection point. Any of those things, just to explain what the result is. Okay, well, spoiler alert, we're going to look at this other option here. What happens when they are parallel and equivalent? So here's an equation, and here's another equation. It's going to look similar to the last example, but I've adjusted it slightly. So two equations and same thing. If x1, y1 is an intersection point, then what must be true? Well, it must be on the first line, and it's also on the second line. Okay, same thing. We're going to mix these together by noticing there's y1, this is y1, and this is y1. We'll substitute this expression, which is in terms of x1, into this equation. That'll get rid of our y1 variable altogether. We'll have a equation with one thing to find instead of two. Okay, let's see what happens. 6x1 minus 6x1 plus 10, and then at the end here, minus 10 equals 0. I think you can see what's going on now. We have 6x1 minus 6x1 plus 10 minus 10. That's 0, that's 0. That means here we have an equation that says 0 equals 0. Well, that's good because that's actually a true thing. Well, let's see what our logic says here. If x1, y1 is an intersection point, then 0 equals 0. This is going to be true regardless of what x1 and y1 are. So another way to say that, this is always true for every point on each line. That is, any point that you choose on one line is a point on the other line. So we have this situation. So if I choose a point, I can say, yes, that's an intersection point. If I choose another point on a line, that's an intersection point. They're all intersection points, which means the lines just directly overlap one another. So every x1, if you like, will give a y1 that is an intersection point. And so the lines are parallel and equivalent. Now you might say things like the lines are the same line, the lines are identical, the two equations represent the same line, they're just written differently, and you can rearrange this one and it'll end up looking like that one after you simplify it. So those are the two other things that can happen. So let me just recap from the very beginning, from part 1. The two lines can intersect in a single point, and when you do the substitution, you'll get a single value for x1 or y1 and solve for the other. You can find that something, if you assume there's an intersection point, then something false will occur, so there must not be an intersection point. Or you can assume there's an intersection point and find out that it doesn't matter which value you pick, on which point you pick on the line, it's always an intersection point, and that's the third situation. Okay, I hope that has been helpful, and let me know if you have any questions. Thanks.